Today is the start of a series of videos on solutions. Up till this point, we've been talking mostly about pure substances and how pure substances behave, but solutions are mixtures of more than one pure substance. They have their own particular terminology, and there's a way that we can keep track of certain characteristics of solutions. But the chemical behavior of a solution depends mostly on what is dissolved in the solution and what the solution's principal component is, or the solvent. We're going to be looking mostly at physical characteristics of solutions as we go through this series of videos. First of all, we're going to establish some definitions of some terms so we can talk about this intelligently. A solution is a homogeneous mixture, and in this mixture, all the particles are on the scale of atoms or molecules, so about atomic size or molecular size. So these particles are around 0.05 of a nanometer up to about 1/4 of a nanometer in size. Because the particles are so small, they're not individually distinguishable, and so you can't really tell where one part of the mixture stops and the other part of the mixture begins. And so we use the word homogeneous to describe it. Homo means same, and geneous comes from the word that means form. So it looks like the same form throughout. By our eye, we can't tell that it's a mixture. The solvent in a solution is the medium in which all the solutes are dissolved. If water is the solvent, then we call the solution an aqueous solution. There may be more than one solute, and the solvent is typically the biggest component of the solution, the biggest part of the mixture. Solutes are substances that are dissolved in the solvent to make the solution. And solutes may be solid. An example would be when we dissolve salt or sugar in water. The solutes might be liquid. An example of that would be ethanol, C2H5OH. When that's dissolved in water, you have alcoholic beverages. Or antifreeze is another example of a liquid dissolved in another liquid. And the solutes may be gas. For example, in soda pop or in beer, in both of those cases, one of the solutes is carbon dioxide, which is a gas. And a solution may have multiple solutes. It can have more than one solute in the same solution. Soda would be a good example. There are liquid syrups dissolved in it. There are solids like sugar dissolved in it. And there are gases, principally carbon dioxide in soda pop. Saturated is another term that you hear when you're talking about solutions. Saturated means that the solution process has reached a dynamic equilibrium. So what's happening in the solution formation is that you have solute and you have solvent, and the solute and solvent go together and they make solution. But anybody who's ever dissolved sugar in iced tea, for example, realizes that eventually you can't dissolve any more sugar in the tea. And so this process is reversible and it reaches dynamic equilibrium. When that happens, you have what's called a saturated solution. In other words, this means the maximum quantity of solute possible is dissolved in the solvent. Now, that depends on a few factors. For example, it changes as the temperature changes. And you probably have experienced that if you try to dissolve sugar in hot tea, you can dissolve a lot more than you can in cold tea. And then pressure also has a factor. And we're going to talk about that in a later video. A supersaturated solution is one that has an amount of solute dissolved in it that's greater than the saturation quantity. In other words, you've gone beyond dynamic equilibrium under normal conditions. And you can only do this by a trick of temperature change that we can talk about later on when we investigate what's the effect of temperature on creating a saturated solution. Why do solutions form? Well, there are two main factors. One of the reasons that solutions form is just a simple look at randomness. At the left-hand side here, we've got an example of two different kinds of particles. Let's say that the purple ones are solvent particles and the green ones are solute particles. Right now, they're separated from each other by a boundary, but of course, they're in constant random motion. This is a still picture, but if it were live, you'd see these particles moving around, constantly randomly bouncing off of each other and the walls of their container and the walls of the boundary, because that's the kinetic theory of matter that we operate under in chemistry. Now imagine that the boundary is removed. You remove the boundary and you walk away and you come back 10 years later. It would be, you can probably easily imagine this, extremely unlikely that by pure random chance these particles happen to be not mixed together. In other words, all the greens are on one side and all the purples on the other side. There would have to be something weird going on between these particles to keep them from mixing together. A mixture is more random than an unmixed solute and solvent. And what's more random is more likely. Think about a deck of cards. There are 52 cards, and when you buy a deck of cards from the store, they're arranged by suit and they're arranged by value. How likely would it be that that would happen randomly? Well, let's think about just 4 cards. Let's imagine that we just have 3 cards. I'm going to label them 1, 2, and 3. How many possible ways could we arrange them? Well, one possibility is what I have drawn here, 1, 2, and 3. But I could also have 1, 3, and 2. I could have 2, 1, 3. I could have 2, 3, 1. And I could have 3, 1, 2, and 3, 2, 1. So in all, I have 1, 2, 3, 4, 5, 6 possibilities if I have 3 cards. Imagine that I have 4 cards. Card 1, 2, 3, and card 4. Well, what are my possible arrangements? I could have, just like I have, 1, 2, 3, and 4, but I could have 1, 2, 4, 3 as well. I could have 1, 3, 2, 4, and I could have 1, 3, 4, 2. I could go 1, 4, and then have 2, 3 after it, and I could have 1, 4, 3, 2. Or I could start with 2, and I could have 2, 1, 3, 4, or 2, 1, 4, 3. I could have 2, 3, 1, 4, and 2, 3, 4, 1. I could have 2, 4, 1, 3, and 2, 4, 3, 1. Or if I started with 3, I could have 3, 1, 2, 4, or 3, 1, 4, 2. I could have 3, 2, 1, 4, and 3, 2, 4, 1. I could have 3, 4, 1, 2, and 3, 4, 2, 1. If I started with 4, I could have 4, 1, 2, 3, or 4, 1, 3, 2. I could have 4, 2, 1, 3, or 4, 2, 3, 1. I could have 4, 3, 1, 2, or 4, 3, 2, 1. And I think those are all my possibilities. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 possibilities. Oh, with this one, there's 24. So 24 possible ways that I could arrange 4 cards. Now, what's the pattern here? What does 3 and 6 have in common with 4 and 24? Well, if I think about 3 times 2 times 1, that's equal to 6. So we could say that 3 factorial is the number of possibilities. Does that hold true here? What's 4 factorial? It's 4 times 3 times 2 times 1. Well, 3 times 2 times 1 is 6, times 4 is 24. And so the answer is, if you have n cards, you're going to have n factorial different possible ways of arranging it. So imagine now that you have 52 cards. There are 52 factorial different ways of arranging a deck of cards. Only one of those possibilities is the ordered arrangement that you get when you buy a deck. So just thinking about that simple example with only 52 possibilities, the numbers are staggering. 52 factorial is equal to 8 times 10 to the 67th. So your odds of getting an ordered deck randomly by throwing the cards up in the air and just sweeping them together are 1 in 10 to the 67. So a billion, 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 billion chances, only one of those is the right arrangement. Now imagine that you had a mole. Imagine you had 10 to the 23rd factorial. That number would be incomprehensibly small. The odds that a solution would not have formed by random mixing. So the more random possibilities exist, the less likely it's going to be that you're going to find separate solute and solvent, the more likely you're going to find a random mixture. And that's exactly what we see. Now, there are some substances that you can throw together and leave for a very long time, and they still don't form a solution. They don't dissolve into each other. So there's another factor there, and that is the attractions that exist between the solute and the solvent. Here's an example. Ethanol and water. These dissolve into each other very well. And here's why. If we look at the structure of ethanol, we see OH bond, and of course this has lone pairs on it. And water also has lone pairs and OH bond. So hydrogen bonding exists between ethanol and ethanol, but it exists between ethanol and water as well. So when the solvent and the solute have similar intermolecular forces, they're attracted to each other, and a solution is likely to form. So there's a kind of a saying that goes along with this that says like dissolves like. And like dissolves like means polar dissolves polar, as we can see here, or something that hydrogen bonds dissolves something that hydrogen bonds. Let's look at another example, benzene and carbon tetrachloride. Benzene is a nonpolar molecule. It has only C, C, and CH bonds. So that would be nonpolar regardless of shape. Carbon tetrachloride has polar bonds. The carbon-chlorine bond is polar, but it's a tetrahedral shape, and that cancels out all of the polarity of the individual bonds. And so these are both nonpolar molecules. Because a benzene is no more attracted to other benzenes than it is to carbon tetrachloride, because they both do the same kind of intermolecular forces, benzene and carbon tetrachloride dissolve in one another easily. Here's another example, water and HCl. Hydrochloric acid forms when HCl molecules dissolve in water. Why does that happen? Well, HCl is a polar bond. Here's the dipole. Chlorine is on this end, and it's the more electronegative of the two. So the positive H ends of these water molecules are attracted here by dipole-dipole interactions, and the negative O ends of these water molecules are attracted to the positive H end of the HCl. And so because there's a strong attraction between HCl molecules and water, HCl can penetrate the water and become part of a solution. It's harder to see with more complex molecules, but it's still true. This is glucose, the thing that we see in the middle. The blue things are carbons, the grays are hydrogens, and the reds are water. We see an OH bond here, and that can make hydrogen bonds with a water molecule. And the same thing is true right here. Hydrogen bond. A hydrogen bond can form here. A hydrogen bond can form here. And so in those places, water molecules can attach to this. So there's an attraction between glucose and water, just like there's an attraction between water and water. And so glucose is able to penetrate the structure of the water molecules and form a solution. Now if we take a look at benzene and water, we see that benzene and water do not form a solution, and here's why. Benzene is attracted to water because water does London forces just like benzene does. But if you imagine benzene trying to get inside a bunch of water molecules that are all attracted to each other by very strong hydrogen bonds, it's just not going to be able to penetrate that structure. It would have to move water molecules out of the way and attach to individual water molecules. It can't do that because it doesn't have the ability to hydrogen bond to water like waters can hydrogen bond to each other. And so a benzene will never dissolve in water. Now the like dissolves like rule kind of oversimplifies this, I think, and it kind of makes it sound like benzene isn't attracted to water and doesn't want to dissolve in water molecules. It is attracted to water. It's just not attracted to water as strongly as other waters are attracted to water, and so it can't get in there. So when the IMFs are quite different from each other, a solution is unlikely to form, and we see that in this example. This is what a crystal of sodium chloride might look like. You can see there are sodiums, which are shown here in silver. They're positive, and then the chlorines are green, and they're negative. If we dissolve sodium chloride in water, like this salt shaker is shaking some crystals into water, if you could magnify that big enough, here's what you'd see. The positive H ends of water molecules would be attracted to the negative chlorines, surround them, shake them loose by their random motion, and then pull them away from this crystal. On the same hand, the negative O ends of water molecules would surround the positively charged sodiums and pull them out into solutions surround them. And as this process goes on, all the outside particles would eventually be pulled away, and then the salt would completely dissolve. So as we saw in this example with sodium chloride, a polar solvent will be attracted to charged ions and dissolve them as well. Well, as we know, there's almost always something going on with energy when there's something going on with matter, and so solutions are no different. Just as we saw phase changes with solids, liquids, and gases absorbed or released energy as heat, there are also heats of solution. So the heat of solution is the enthalpy change that's associated with forming the solution. That's called the heat of solution, or delta H of solution. For a solid solute dissolving in a liquid solvent, so this would be like sugar or salt dissolving in water, the most common kind of solution formation we're familiar with. Imagine using Hess's law to visualize a two-step process to make the solution occur. First, you have to break up the crystal. So imagine that we take these particles, so we have solute as a solid, and we vaporize it, we sublime it, make solute as a gas. That's always going to be an endothermic process. In fact, the amount of energy is going to be the lattice energy that we'd have to put in there. So the solid particles are vaporized, first of all. And then the next thing that happens is energy is released as these attracted solute particles enter the solvent to make a solution. Well, that process is going to be exothermic as energy is released by the attractive particles being allowed to go back together. How much energy is released is going to depend on the attractions between the individual solute and solvent particles. So the delta H of solution is the difference between what you started with, solute and solvent, and what you ended with. How big is that? It depends. So it might be exothermic if more energy is released when the solution forms than it took to break up the solute originally. It might be endothermic if it's the other way around. If less energy is released by solution formation than is input to break up the solute. So this delta H value of solution for this process is indeterminate and depends on the particular solution that you're making. Let's imagine a liquid solute dissolving in a liquid solvent. So this would be like antifreeze dissolving in water. Here we can imagine a three-step process. First of all, you start out with solute and solvent as separate substances. The solvent has to expand a little bit in order to make room for the solute. So the solvent expansion is going to be endothermic. Delta H for that process is going to be positive. The solute is also going to have to expand a little bit, just like we saw in the last example. So solute expands in order to fit into the spaces in the solvent. That is also going to be an endothermic process. You're taking particles that are attracted to each other and pulling them apart. Then the solute and solvent are going to go back into each other and form a solution. Is this exothermic or endothermic? The heat of solution is negative. In other words, it's exothermic if the intermolecular forces between the solute and the solvent are bigger than the intermolecular forces between the solute and other solute particles. The heat of solution is positive. In other words, it's endothermic if intermolecular forces between the solute and other solute particles are bigger than the intermolecular forces between the solute and the solvent. So in other words, you have to put energy in to make them dissolve, that you don't get out. And if they happen to have equal attractions for each other, then delta H of solution is 0, and this is what we call an ideal solution. The last possibility would be a gaseous solute in a liquid solvent. We can imagine this as a two-step process. The first thing you have to do is expand the solvent. So here's our solvent, and we're going to pull the particles a little bit farther apart than they are. So the solvent expands, and that's going to be an endothermic process because you're pulling attractive particles apart from each other. And then the gas is going to enter those spaces in the expanded solute. Well, this is always going to be a highly exothermic process because you have particles that are attracted to the solvent that are very far apart from the solvent. So delta H here is going to be very negative, quite negative. And so in almost all cases, the delta H of solution is going to end up being a negative value. So this is almost always exothermic. Now, what looking at these heats of solutions is valuable for is imagining what would happen if you change the temperature around a solution formation, especially if it's at dynamic equilibrium. Is that going to make more of it dissolve or less of it dissolve? Depends on the particular substance that you have, but there are some general rules, and we'll look at those in our next video.